Welcome to another video on velocity profile. So this time we are talking about the velocity profile of a falling film. So when we allow a layer of liquid to fall through a vertical wall due to gravity, so what will be the velocity profile? When we talk about velocity profile, we want to obtain two parameters. One is v z x, velocity in z direction, means downward direction at a location x. Of course we can just say simply as a v notation. Here we are going to use notation v, but while writing v we'll have to understand that velocity in z direction at location x. So now for that one you just note this particular diagram. So this is the wall, vertical surface of this wall. Okay, so now, and this is the outer surface of the falling film. So now our zero starts here, means at the outer surface of this falling film the coordinate is 0, x coordinate is 0. So this is the x-axis. So at the interface the x coordinates value is same as that of the thickness of the layer. So at the interface the x value will be equal to thickness, and this is the downward. We are showing z in downward direction. It is slightly different from your convention. Actually conventionally z is shown upward, we are showing z downward. Okay, x from left to right and z from top to bottom. Okay, so now we are interested to obtain the expression for z directional velocity at a location x from this free surface, and another objective is to find the average velocity as a function of the maximum velocity. So now here we will have to identify that this maximum velocity will be occurring at the surface and minimum velocity will be occurring at the interface. Okay, minimum velocity means which will be 0 and maximum velocity will be Vmax. So now what is the ratio of Vmax to V average? So we are going to get it. So this assumption is that the wall or plate on which the liquid film is sliding is quite wide. This width of this wall, just like actually what we in real sense whatever wall we get, so the width of the wall is quite great. Okay, so therefore we can say that actually this means flow is happening only in means z direction, so nothing is changing in y direction. Okay, it is independent of variation in y direction, and the width of the wall is w. It is a one-dimensional flow behavior and film thickness is known to us. Okay, so now within this film, okay, we are anticipating this velocity profile to be like this. Okay, we'll likely to will be getting the exact means expression for this profile, but we are sure that actually at this outermost surface it will be maximum, and at the innermost surface, not innermost surface, okay, at the interface it will be 0. Okay, so now in between it, where actually see this fluid is flowing, we are considering one element. So the element is having a thickness of, or in terms of in x directional thickness of delta x, and across the surface the thickness is w and height is delta z. So we are considering an element of delta x, delta y, and w. That is the 3 dimensions. Now we'll have to identify the forces acting on this element. So there will be 2 forces acting on this element. One is the gravity force. Gravity will be pulling it down. Now this gravity force will be dependent on this mass multiplied by the z value. Okay, so mass will be equal to this volume, means product of these 3 values or these 3 dimensions multiplied by rho into z. So that will be the gravity force. Then since it is moving downward, therefore the out layer of fluid in this direction is moving at higher velocity, whereas fluid near the wall is moving at lower velocity. So this outer layer means this side's fluid, left side's fluid, is dragging it downward in the same direction as that of your gravity, and is a layer of water means fluid which is towards the wall side, it is holding it back. Okay, therefore we are computing the shear stress that is occurring in z direction. Now let us think about positive z direction. So this is positive z direction at a location of x. So now let us note the notation or subscript used here, tau xz means x directional shear stress at due to z velocity and at location x. So this is moving downward, we are taking it positive. Now another value, whatever is here, you see, we can show that, you see, up to here this distance is x, then this will be x plus delta x. At the second point it is x plus delta x, but it is acting upward. So now net shear force will be this, whatever is acting downward minus whatever is acting upward multiplied by the area of action of this particular force, shear force. So action of area of action for the shear force will be this height multiplied by depth across this surface. That is, you see, the depth perpendicular to the surface of this page. Okay, so that is W. So delta z into W. So then the net force acting will be the shear force downward plus gravity force downward. Now net force will have to be 0 because we are saying that it is moving at constant velocity. There is no acceleration. So net force is equal to 0, and we can manipulate it slightly by dividing it both the sides by this 3 dimensions, multiplication of these 3 dimensions, or the volume of this element, both the terms, then we get this particular expression. And what we get is that derivative of space derivative of x directional derivative of tau xz is equal to rho z. So now after we get this expression, then we can integrate it. So if we integrate it, we are going to get that tau xz is equal to, in as doing it as an indefinite integral, then what we are getting, rho z x plus the c. So this is a coefficient of integration, constant of integration, sorry. So now we can eliminate the constant of integration, then we will be getting tau x equal to rho z x. So for elimination, actually what we say, that at value of delta, the thickness, the velocity is 0. It means c will have to be 0. Okay, so constant of integration here is 0. So therefore tau x is equal to rho z x. Now we are determining this profile for your Newtonian fluid. Okay, so for Newtonian fluid, we know what is tau xz. Tau xz will be minus mu rho vz, sorry, delta of del vz del x, or space derivative of vz is equal to rho z x. So then we do minor rearrangement, del vz del x is equal to rho z by mu into x, and then we are integrating it after separation of variables. Left hand side it is for vz and right hand side it is for x, means how velocity varies against x, we are interested for that one. So left hand side's integration again by indefinite integral. So vz will be equal to the conventional integration of this one plus constant of integration. Now we'll have to eliminate this constant of integration. For eliminating this constant of integration, what we do, we say that at thickness, this all, so this one we are applying it now for eliminating this C1. So what we are seeing is that V is equal to 0 when x is equal to thickness. So then we get this term for C1. C1 is equal to rho z by 2 mu into thickness square. So then when we substitute this value of C1 here, then we get Vz is equal to rho z by 2 mu into thickness square multiplied by 1 minus x by thickness square. Now you see x by thickness is basically, see, you can call it relative position. Okay, so now let us say it is a half midway or at the midpoint. Midpoint means x by thickness will be half. Okay, so that you can very easily interpret it. So means actually, see, now you see what it is. So this is the Vmax. First of all, you see, this is the expression for Vz. So that was the actually, see, first objective of our discussion, that what is the velocity profile. So we have got this expression. Now out of it, you see what I was saying, that what is this one? Rho v by 2 mu into thickness square. So this is maximum velocity occurs when x is equal to 0. When x is equal to 0, v is equal to v maximum. So therefore, x is equal to 0 means this second term vanishes. So only this term remains. So that is the actually Vmax. So this is the expression for Vmax, V maximum. Okay. Now we can, in terms of V maximum, we can express the value of Vz. So Vz is equal to Vmax into 1 minus x by thickness square. So again, the same definition as we have used earlier, that how to obtain a expression for V average. Okay. So what we are doing is, we are flow area is at the denominator, numerator is the net amount of fluid flowing. Okay, net amount is basically the velocity into area, and that is integrated for the whole thickness. So from 0 to the thickness. Okay, so W is the constant that is coming out. Okay, so then we are getting expression for Vz, which needs to be integrated V maximum by thickness into integration of this particular term. Okay, then we are going for a very, let us say, elaborating it in a very, let us say, simplified manner. Let us say we are defining a new variable y is equal to x by thickness. So if then we can replace this, all the variable x we can replace with this variable y now. So wherever x is there, we are going to substitute this term. Similarly, wherever dx is there, we are going to substitute by this term. So then when we are changing this definition of the variable itself, so the limit will also change. So initially, when x is equal to 0, this y will be 0. When x is equal to thickness, so this term, because thickness by thickness means 1. So now this limit for this integration will be 0 to 1. Therefore, V average is equal to V max into 0 to 1, 1 minus y square dy. So then V max into y minus y cube by 3, 0 to 1. This is the range. So when we just simplify it, for 0 it will vanish, for 1 it will be 1 minus 1 by 3, which becomes 2 by 3. 2 by 3 into V maximum. So this is the second objective of our discussion. So what we can say is that actually, say, we have got the expression for V average, which is basically 2/3 of the V maximum. So now this is the case, we can compare with our, you see, pipe flow, where this ratio was half. Here it is 2/3. Okay, so that's all as far as this part is concerned. Thank you.